Hello everybody. You may have noticed that our big quiz this week is going to be a little different than ones that we've done in the past. You guys are actually going to be writing out some hand drawings and then uploading them instead of just going through the regular quiz in Canvas. In this video, I'm hoping to help you guys get started with that and give you kind of a sense of why we would go through these steps with these different molecules, what information we're getting each time, and how these things can actually be pretty useful to us as we move forward. So what we're going to do is we're actually just going to go through the very first one that you guys are going to be doing. So in order to get full points, you're going to have to hit all of these different bullet points here. And we'll just start with the first one. We need to draw out a Lewis dot structure for our sulfur dibromide here. And in order to do that, we're going to start by just identifying all of the different atoms that are in that species there. So we got a sulfur, we've got a bromine here, and we can just on the other side toss in our second bromine there. The next thing that we need to do is decide how many valence electrons each one of these gets. And the way that we're going to go about doing that is by looking at our periodic table. And basically what we're going to do is we're going to count from the left over to the various, whichever one we want, and that's going to be the number of valence electrons that we get. Now we're not interested in counting any one of these because these are d orbitals. We're just interested in the electrons that are in the s and p orbitals. So let's start with sulfur. We're going to go 1, 2, 3, 4, 5, 6 for sulfur. And for bromine, we're going to go 1, 2, skip a few, 3, 4, 5, 6, 7 for bromine. Now when I come back here, in order to draw out my Lewis dot structures, I'm going to recognize that I get 4 spots around each one of the atoms. And these represent those 4 orbitals, a 1s orbital and 3 p orbitals. And I'm going to start by putting 1 electron in each one. So I go 1, 2, 3, 4. And then I can start pairing them off 5, 6. Now I can do the same thing for bromine. I'll start off 1, 2, 3, 4, 5, 6, 7. And then I'm going to do the same thing for this bromine. 1, 2, 3, 4, 5, 6, 7. Okay. Notice I didn't do the whole 1-to-1 thing, but that's just because I knew that this bromine was going to be the same as this bromine, so I just filled them in there. Now what we need to recognize is that I drew them slightly off center here. This one here is a single electron associated with sulfur, and this guy here is a single electron associated with bromine. And what's going to want to happen is they're going to want to get together and be shared between the two. Okay. Forming a single bond between bromine and sulfur. Over here, the same thing's going to happen. They're going to start to be shared between the two. And they're going to form a single chemical bond between sulfur and bromine over there. Now if I want to write this out a little bit more explicitly, I can actually do the sulfur there, draw those out as bonds, do our bromine here, do our bromine here, and then write in all of our lone pairs. And so either of these answers would be appropriate to get you full points for drawing of the Lewis dot structure. The next thing we need to do is take a look at the electron pair geometry And it has to have vectors indicating bond dipole moments. This is a big phrase for us right now. And we're going to use dash and wedge bonds to indicate perspective. Okay, so the electron pair geometry is going to take into account all of the species that are around this central atom here. Okay, so it's going to take into account the two bromides, and it's going to take into account the two electrons there, or lone pairs there. And to do that, we have a table in our book that we use during the VSEPR lab. Okay, and the electron pair geometry that we're going to see is going to be coming from this first column here. And if we have four things bound to it, we can see that we're going to get this tetrahedral shape right here. It also shows us how to use the wedges and dashes in order to write it out. So let's see if we can recreate that here. We can do a sulfur. We'll have this guy coming out here. I'm going to choose to make that a lone pair. It doesn't really matter. We're going to have this guy here. That's going to have a lone pair on it. Just so that you know, this is to kind of draw a perspective, like you might see on like a painting of something down a hallway or something. This is meant to show that this is coming out of the plane of the paper, and that this would be going into the plane of the paper. Now I'm just going to add my bromines. Bromine there, and a bromine there. And if I'm a good chemist, I'm going to also add in the lone pairs on those guys. Okay. We know that this is tetrahedral. Now, the last thing we need to do is add our bond dipole moments. So what is a dipole moment? And what is a bond dipole moment? So a bond dipole moment gives us an indication basically of how these electrons are being shared around these bonds, right? Are these electrons staying mostly with sulfur? Are they staying mostly with bromine? You know, where is that electron density going? All right. And whether the electron those electrons want to stay mostly with bromine or stay mostly with sulfur has to do with a value called electronegativity. All right. This is the tendency for an atom to want to draw electrons towards it. Okay. In order to show this, we're going to use what we call these dipole moments, and those are vectors. A vector is a mathematical entity. There's a lot of math that you can do with it. In this context, though, a vector is only going to be an arrow, and that arrow is going to have a direction. So a beginning and an ending. And it's going to have a magnitude. Okay. The direction of this arrow is going to point from the atom of lower electronegativity towards the atom of higher electronegativity. And the magnitude is going to be based on the difference in electronegativity between the two atoms. Now, this begs the question, how do I know what the electronegativity is of a specific atom? And how am I going to know what their difference is going to be? And that's actually a pretty easy thing, because electronegativity is a measurable quantity. So that means that we have just measured them all. And you'll find that there's this figure 7.6 in our book, and it has all of the electronegativity values for all of the different atoms. Okay, so we can just go and look them up. For instance, we see that sulfur is at 2.5 and bromine is at 2.8. So bromine is the more electronegative atom. The difference between them is 0.3, which isn't a huge difference, but it is some kind of significant difference. So you can always look these up, but it is important to note that there's a trend here. The lowest values are going to be found in the bottom left of the table, and the highest values are going to be found in the top right of the table. So they kind of go up as you move from left to right up diagonally like that. So now we know that sulfur is the less electronegative atom. Bromine is the more electronegative atom. So our arrow is going to point along this bond towards bromine. And to indicate that it's a dipole moment, we usually put that little horizontal slash on it, right? Like that. And we're going to have another one here. It's going to have the same sort of length because we have the same sort of difference in electronegativity here. And that is going to be our bond dipoles. There's an extra bit of notation you're going to see in the future around this, which is that because this electron density is being drawn down like that, what you're going to see is that sometimes we want to indicate that there's a partial negative charge here. There's not a full negative charge, but he's getting more than his fair share of electrons. There's a partial negative charge. So you put this little Greek letter delta here with a little negative sign. And we can give this guy 1, 2, just to indicate that these guys are partially negative. Now, because those electrons are coming from sulfur, sulfur is going to get a partial positive charge there. So this kind of thing right here would get you full points for the electron pair geometry with the bond dipole moments. So now we get the general gist of how this is arranged here. Okay, but the thing is that chemists, we're really lazy, right? So we're not going to draw out all of this stuff every single time we need to draw out our molecules. We want to condense this notation down a little bit and just get a sense of how this arrangement is different than, say, another arrangement that might also not have these lone pairs and stuff on it. And that's where the molecular geometry structure comes in. So our next task here is a molecular structure with a vector indicating dipole moment. Use dash and wedge bonds to indicate perspective. Now, you'll notice that now we have dipole moment, not bond dipole moment. These are different things, and they are unfortunately very similar to each other. Okay, while the bond dipole moment gave us some information about what was happening within this molecule, the dipole moment is going to give us an indication of how this molecule is going to interact with other molecules. So this is what we would call intramolecular interactions, and this is going to give us an indication of intermolecular interactions between two molecules. So to do that, basically what we're going to do is we're going to condense down our notation where we just have sulfur with its 2 lone pairs here, not drawn out explicitly like that, and we're going to explicitly draw out our bromines, indicating the shape that we now know that they have, that it's not this straight linear thing, but instead there is an angle between them. Okay, and then we'll finish that off with our lone pairs. Now we just need to give this a name. If we go back to our table, All we need to do is come down to 4 and then over to where we have those 2 lone pairs there, and we see that we have the name of bent, okay, or angular. I always see it called bent though. Simple enough. We'll give it our name, bent. Now we need to figure out what our dipole moment is going to be. The dipole moment of the overall molecule is going to be the sum of these 2 vectors here. Now, to indicate this, I want to use some colors here, because I think that that's helpful. And I'm just going to start by redrawing my dipole moment. So I'm going to draw this one here, and I'm going to draw this one here. Now, to get the overall dipole moment, what I want to do is I want to take this tail and have it start right at the S right there. I want to imagine moving that over there. So I'm just going to draw it a little closer to it so that that tail is right on the midline of our sulfur. And I'm going to draw it out here like this. Okay, now I'm going to imagine moving this one so that its tail is right at the head of the first one. Okay, so this is how we can graphically sum vectors. The sum is going to be when we an arrow that starts at the tail of the first one and ends at the head of the last one. Now I can get rid of these bond dipoles because I didn't really need those. Those were just for my purposes of demonstrating. And we have the overall dipole moment of this molecule. And that's pretty much it. We've hit all of the things that we wanted to hit. We're now able to see that the Lewis dot structure gives us a sense of how things are connected, where those lone pairs are. The electron pair geometry gives us a sense of the overall geometry of the molecule, okay, and allows us, we can then identify where our bond dipoles are. And then we can condense that down a little bit to give us a sense of the overall molecule here. And it has this bent structure. And then we can add our bond dipoles together to get the overall dipole moment. And this is going to give us an indication, as we'll learn later, about how the different molecules are going to interact together.